Hello, my name is Frank Lenzmann. I'm a researcher in solar energy since more than 20 years. I work at the Dutch National Technology Research Center. One of the focus areas of my research is PV sustainability. The presentation, which you will see now in the upcoming slide set, together with my voice, is about the status and innovations of PV recycling. So lean back and stay tuned. Here's an overview of my talk. At the center of it, in points 3 to 6, I will obviously talk about innovative solutions in PV recycling. This is in essence a preview of a report that will be published until the end of the year by an international experts group. In points 1 and 2, I will give you an introduction to that topic, and in point 7, some conclusions. Let's start by having a look at this world map here that is color-coded. The colored countries show you those areas in the world where most of the PV installations are being put up today. This is obviously Southeast Asia, that's the light green color, and that's also Europe, that's the dark blue color, and North America, dark red. And on the right-hand side of the map, you see a bar diagram, and there's two takeaways from that bar diagram. One is, if you look at the x-axis, which is in millions of tons, that the PV waste volume will be very significant in the next few decades. It's going to be on the order of tens of millions of tons. That's one takeaway message. And the other one is that, not surprisingly, this PV waste will occur exactly in those countries where most of the PV installations are being put up today. Now, one very important and interesting thing to note is that if you look at the end-of-life value of PV modules, that there's two components, namely silicon and silver, that represent only a very small mass fraction in the PV module, but they represent a very high end-of-life value of that PV module. Almost 2/3 of the end-of-life value of a PV module reside in these two components, silicon and silver. And that obviously means that it's very interesting from an economic point of view to focus on the recycling of silicon and silver from end-of-life modules. But not only from an economic point of view, also for environmental reasons, this is a good target. Now, if we look at the state of the art today of PV recycling, we can state two things. One is that unfortunately only around about 10% of all end-of-life modules today end up in any recycling stream at all. That's those PV modules that are in legal frameworks that actually make PV recycling mandatory. And the other 90%, they end up unfortunately on waste yards. And the other point to see here on this sheet is that those 10% that do end up in PV recycling, they are recycled by only very basic, simple techniques such as shredding, crushing, and sorting. And these simple techniques, they do allow to recycle more than 80% of the PV module weight. But those components are unfortunately only the lower value components, namely the solar glass, the aluminum from the frame, the copper from the cables, and the junction box. That's 80% or more than 80% of the PV module weight. But unfortunately only around about 1/3 of the value, as I showed you on the sheet before. The two components that I talked on the earlier slide, silicon and silver, they are not recycled with the state-of-the-art techniques. They end up on landfills or in waste incineration plants, and they represent, as I said before, only a very small mass fraction of the PV module. Here in this diagram that you cannot read, my apologies for the poor quality of the sheet. The only thing I want to show here is, with the red arrows, the state-of-the-art PV recycling. It starts with the arrows that lead to the right in the upper part of that diagram.
And that is simple disassembly, mechanical disassembly techniques. And they allow to, disassemble the aluminum frame, the junction box, and the copper cables that can then be brought to some secondary materials recycling. And the arrows that lead to the left and then around to the lower red frame here. That is the shredding, crushing, and sorting techniques I talked about before, and they lead to contaminated glass cullet that is only possible to use for low value glass applications such as foams and fillers, for example. The blue frames that you see also in this diagram, they show advanced PV recycling techniques, and this is what I will talk about in this presentation. Now we talk about innovative solutions, and these innovative solutions we will publish in a report. I said that in the introduction also. And this report will use a meaningful analytical framework that I will show to you in a moment in order to measure the innovations, to make them a little bit comparable with each other. And it is important to point out that the scope of the report is really limited to the recycling of silicon and silver from either from production waste or from end-of-life PV modules. It does not cover the PV module delamination. This is a different area that is covered in other reports. So the focus is on silicon and silver recycling. The analytical framework that we apply in this report uses a reference method. I will talk to you about this method in a moment in order to measure the innovations with respect to this reference method. It specifies in general terms what kind of technique is being used. Is it wet chemistry, for example, or is it something else? It measures, as I said, the innovation with respect to the reference point. It specifies, and we think that's important, the technology readiness level. That's important in order to compare apples with apples instead of apples with pears. One should only look at, let's say, compare techniques that are on a similar technology readiness level. Otherwise, it makes no sense. And we also specify quality levels and yields of the recycled silicon and silver, if possible, if this information is available. And environmental characteristics. The technology readiness level, for those that may not be familiar with that term, most of you are, so I keep that very short. Technology readiness level 1 means that a technique is in the very, very early research stage, something like a proof of principle, and technology readiness level 9 is something that is really in industrial operation. And everything in between are different levels of development. Now, the reference method that we chose is the so-called FRELP technique. FRELP stands for Full Recovery of End-of-Life Photovoltaics. Again, the diagram that you see here on the right-hand side, you cannot read the details, and that doesn't matter. Because the only thing I really want to point out here is that a lot of information about the FRELP process is published, detailed information, and the lower frame, the lower red dotted frame that you see here in this diagram, that is the part of the FRELP process that deals with silicon and silver recycling. And so the details that are published about the FRELP process include also quality levels of the silicon and the silver. It is a technology that has been developed to a relatively high TRL level because there is a pilot facility, or at least was a pilot facility, that needed to be closed for economic reasons because there was simply not yet enough PV waste volume. But as I showed you, that will soon change. And let's now look on the next sheet a little bit more in detail into this FRELP technique using the analytical framework that we apply. So in short, this is a wet chemical technique that uses acid leaching with filtration and electrolysis. The technology readiness level is quite high. We estimate it as on the order of 7. And that is due to relatively high throughputs that can lead, for example, to 0.7 kilograms of silver per hour. That's a relatively significant amount. The silicon and the silver that come out of this process are on quality levels of metallurgical grade for silicon and secondary silver production for the silver. And regarding the environmental aspects, that there is certainly downside in the FRELP process. There's a lot of chemical waste that is being produced by this technique. For example, 630 kilograms of liquid wastes per kilogram of silver output, and almost 100 kilogram of hazardous sludge also per kilogram of silver output. That's pretty serious waste, chemical waste problems that this technique brings along. So for that reason, it makes sense to look at innovations, and I will be very brief about those. I give you only 2 examples of innovations, because as I said, the report is still in the making. Here I just give you 2 snapshots to give you an idea of how the report will look like. One certainly very relevant snapshot is this technology, also a wet chemical technology based on this peculiar compound here, methane sulfonic acid. You see that compound here on the right-hand side of the sheet. And the innovation and the value proposition of this method is that it holds promise in reducing actually the liquid chemical waste, because this methane sulfonic acid has the nice property that it can kind of dissolve the silver from a matrix. In other words, that will be the silicon wafer, by forming a compound with it. And then it sort of releases the silver again under the action of hydrochloric acid. And then you can collect the silver as silver chloride. And in this way, the methane sulfonic acid is some kind of a chemical shuttle that can be used over and over again. Not eternally, but for quite a lot of cycles. And you see here some references also that in which you can find more information about this intriguing and certainly very promising wet chemical approach to improve on the reference FRELP process. Another example here, I don't want to say is too relevant. It's very, very early stage research that we did ourselves actually a few years ago. That is an approach, just one example of a an approach that does not use wet chemistry. It's a physical separation technique using high frequency voltage pulses. And these voltage pulses can lead to very strong repulsive forces at interfaces. And our hope was that we could blow off, in essence, the silver contacts from the silicon wafers. As you can see here on these SEM diagrams or SEM pictures on the right-hand side, this goal worked out indeed, but only for heterojunction solar cells, where let's say the adhesion force between the silver and the silicon is less strong. For homojunction solar cells, which are by far the largest amount in the market, this approach did not work. So from that point of view, I don't want to promote this technology here as being very relevant at this stage. But nevertheless, it's an example, and there will be more examples in the report, of a technique that does not use wet chemistry. And obviously the promise in that is to avoid chemical waste and to be environmentally more friendly. So that brings me already to the end of my presentation. You can expect the report to come up pretty soon. We are currently evaluating literature lists that we made from the recent past on innovative solutions in PV recycling. We hope to have a draft report by October, November, maybe this year, and a final version by the end of the year. This brings me to the conclusions. I hope I could show you in this presentation that silicon and silver represent really a substantial part of the economic end-of-life value of PV modules, and that for that reason it is important and very interesting and promising to develop advanced silicon and silver recycling techniques that make it really possible to regain those components, unlike the current state of the art. That will be also beneficial then for the environment. And I told you in this presentation also that we are busy currently together with the IEA PVPS working group to write a report about those innovative solutions, and we use a meaningful analytical framework in this report that uses the FRELP process as a reference point. And you can expect this report to be published by the end of the year or early next year, maybe. We'll see. I'm happy to answer questions that you may have, and I'm available for that now. Thank you. Thank you for your attention.